Hi, we're going to start looking at some example problems that deal with how area changes as individual dimensions are changed. Now, if you're a student that I have this year, make sure you've completed the Exploring Section 9.5 before we look at these problems. You can go ahead and pause it. I'll wait for you to come back after you've done that, and that will help put some context to what we're looking at today. Okay, since you're back, I'll assume you've done the exploration, or you aren't here for that. You want to get to right down to the nitty-gritty of what happens to the area of this figure here, a triangle with a height of 5 and a base of 12, if I change the height. So there are a couple of approaches you can take. The most simple approach is to go ahead and calculate the values and see what effect it has on the final answer. So for example, if I were to take this shape and calculate the area of a triangle is half base height. So half base height. And that's going to work out to be 30 square units. Now if I multiply the height of the triangle by a factor of 6, as given in the problem, pretend that's 6 times taller. There's my base of 12. 5 times 6 will put me up at a height of 30 units all by itself. So the new area would be half base, the new height of 30, and that would then give me an area equal to 180. When I compare 30 with 180, I can see that my area has increased by a factor of 6. That's the same factor I used for increasing the height of my figure. So, what we find in this brute force approach is that if I modify a single dimension, the result is to modify the entire figure's area by the same amount. Another example might be to talk about a rectangle, call it 4 by 7, and I'm going to tell you that the height is tripled. Now I could also, for this problem, just as easily say, hey, let's calculate the area of 28, multiply the height of 4 by a factor of 3, tripling it, that will give me 12. Calculate the area of 12 by 7, see what I get. But there's another approach. Since I'm only modifying one measurement, that being the height, I know that that's going to be the one effect I have on the area. So if only one thing is modified, I can conclude that the area will be tripled. Again, as long as only one measurement is modified, that modification carries over to change the area. Remember, this applies to items like polygons. Circles are their own beast, which we'll talk about next. Another example for us to consider is what would happen if both dimensions in a certain figure were modified by a certain factor. So in this case, we start off with a rectangle with a height of 5 and a width of 4. And we're going to double both the height and the width and talk about the subsequent result on the area. Now, we could brute force our way through this by calculating the area of 20, doubling it, so that would mean increasing this by another 5, and making it wider by doubling it as well, so 4 becomes 8. So doubling it in one direction and doubling it in the other. And I can see if my original area was 20 square units, or in this case 20 square feet, I can see that the end result is not that I have simply doubled my figure, I have raised my figure by a factor of 4. So doubling, taking both dimensions by a factor of 2, and that would be in a linear direction, has a net result of increasing the area by a factor of 2 squared, which is a factor of 4. Now, this provides me an opportunity to figure out how much the change in the area will be by changing some of the dimensions without actually having to calculate all of the various factors. Let me explain that a little better. If I stick with this notion that by modifying all of the dimensions of an object it's going to affect the area by that kind of a factor, I don't need to know any of those. I have some box here. I'm going to make it 4 times bigger in both directions. So I can ask myself, what's going to be the net effect on the area? One method would be to draw the whole thing out. I could draw 4 boxes this way, 4 boxes this way. And the subsequent box I'm going to draw is going to have some increased area. And what I see from my sketch, if this is my original area here, my new box, which is 4 times bigger in both directions, is actually 16 times bigger. Now, rather than doing all that drawing, I could also just as easily say, if I'm increasing my dimensions linearly by a factor of 4, it's going to increase my area. That's an inopportune time to get a text message. If I increase my dimensions linearly by a factor of 4, the net result on the area is going to be by a factor of 4 squared, which is a factor of 16. And now I don't actually need to do all of this sketching as long as I remember the rule that modifying the linear distances by an amount will modify the area by that amount squared. So as a quick check, I can ask, if I were to modify the areas by a factor of 5, the distances by a factor of 5, what's the effect on area? Well, that factor will be 5 squared, or a factor of 25 units. Now, circles are an unusual case, and we'll talk about them next.